Greet Greetings everyone. Today we're going to be talking about temperature, heat capacity, and some thermodynamic processes. So we're going to start off by talking about this solar energy plant, Solana, that's built in Arizona. And it doesn't use voltaic cells like to gather solar energy. What it does is it just uses a bunch of mirrors and focuses all that light in order to heat up salt. The reason why it uses salt is because salt has a very high specific heat capacity, and this is needed because we generate a bunch of energy during the day. We collect all the solar energy and store it as heat energy in the salt. But then the demand for electricity is pretty constant throughout the day, and then also at night. People want to keep their homes cool, they're watching TV. So you need to be able to provide them with that electricity when the sun goes down. So you need some way to store that heat. And Solana is a plant where they use this molten salt and is able to keep this salt hot for about a week. We're going to start off by talking about the zeroth law of thermodynamics. Well, first they went through and did laws 1, 2, and 3, and then they go back and said, well, there's something even more fundamental, and that's the zeroth law. And this just says that if you have two bodies in contact, and they're in contact with a third one, and everything's in equilibrium, then everything must be at the same temperature. So it basically means that if TA equals TB, and if TB equals TC, then TA must be equal to TC. So it's an associative property. So pretty simple. Basically, you put things into contact with each other, and if they're in equilibrium, they're going to be at the same temperature. So let's test our intuition about how energy is transferred between objects. So if we just add hot water to cold water, here we're going to ignore this cup, and we just add equal volume to each one. Then what we would expect is that the temperature is going to be just halfway in between. And this will be right. But for a more quantitative way of doing this, we need to consider how the heat energy, this is Q, is transferred between the two of them. So then the heat of the hot plus the heat of the cold is going to be equal to 0. And so instead of doing it for the equal volume, which is less interesting, let's look at this example where we're going to just add 1 part hot to 2 part cold, basically, and then see where the equilibrium temperature is. So Q hot is going to be the mass of the hot water times C times delta T of the hot water plus mass of the cold, C, delta T of the cold is going to be equal to 0. And so right here, since we're dealing with just one substance, the specific heat doesn't matter quite so much. So we're just left with the mass and the temperature change. So the mass of the hot is going to be half the mass of the cold. So we can just put that in. And then delta T is going to be T final minus T initial. And then we're going to have the same thing for the cold water. So we have 1 part cold water, and then now our T final is going to be our, and then we subtract off our T initial, which was 24. So this T initial is 100. So we're just going to solve for T final. So we have 1/2 plus 1, so that's 3/2 T, and then here we have 1/2 times 100, so that's minus 50, and then minus 24 equals 0. So this tells us that 3/2 T has to equal to 74. So then T is going to be equal to 74 times 2 divided by 3, and this is going to be about 49 degrees Celsius. So the amount of heat energy, that's Q, that it takes to raise the temperature, so we're talking about delta T, is going to depend on a couple things. This is our mass and on the type of material where the specific heat comes into play. The specific heat is going to depend very much on the number degrees of freedom in our molecule. So if we look at a monatomic gas like Ne, He, any of these noble gases, then we have 3 degrees of freedom here. We have X, Y, and Z, and we can have kinetic energy in Z. We can have kinetic energy in any one of these. If we look at diatomic gases, like nitrogen or oxygen, if they're very cold, they act just like a monatomic gas. But if we warm them up enough, like room temperature even, then they start to act like they have another 2 degrees of freedom. So they act like they have 5 degrees of freedom. Where these other 2 come from is the rotation. So we can rotate them around this way, or we can rotate them around this axis. So both of these have a moment of inertia of 2 times mass of the oxygen or whatever, then times r squared. You'll notice that we don't have 3 ways to rotate it, because if we rotate it this way, like this, then our I is 0. So we can't store any energy this way. If we heat that diatomic gas really hot, then we open up 2 more degrees of freedom, and these are associated with the vibration. So here we can just look at a couple of our specific heat, and we're going to divide off this KB, just to show you that here we have this 3/2 for all these monatomic gases, and here we're going to have 5/2 for these nice diatomic gases. And things kind of fall apart when we talk about liquids and solids, because how this ideal gas approximation kind of falls flat. But what you can notice is that water has a very high specific heat capacity compared to all these other materials. And this is in units of kb, but if we work with nicer units like joules per gram Celsius, you can see that water is 4.184, and animal body tissue, human body, is about 3.5. It's mostly water. And then coming down to air is still pretty high at 1. And then now we start to get to all these metals. Metals generally have very low specific heat capacity. There are a couple different types of thermodynamic processes. One is isothermal, and it's pretty easy to see that if we held T constant, then P and V are going to be inversely related to each other. So here we have a high temperature, and if we move in this direction, our T is going to increase. We can also have isobaric processes. The way to remember this is a barometer, and so then P is going to be constant. And so if we increase P, we're just going to move on another horizontal line this way. We can also talk about isochoric or isovolumetric processes. Both of these have constant volume, and so as we move in different volume, then we're just going to increase the pressure, but the volume has to be constant. Another kind that's a little bit more confusing are these isoentropic or adiabatic. So this means that the heat that's transferred into the system is going to be 0. And it's actually pretty hard to tell the difference between this curve and this curve. But what you can remember is that this will be a little steeper descent than the isothermal curve. So we're going to play name that process. So we're going to look at this graph and tell the difference between which type of line goes with which type of thermodynamic process. So this right here, constant pressure, so that's our isobaric. And then now we have a straight line vertical, so that's our isovolumetric. Then now we have these 2 curves, this purple and red, and it can be pretty hard to tell the difference between the 2. But the steeper one is usually our adiabatic, and then this one is an isothermal. So what about real-world processes? What if we are boiling an uncovered pot of water on the stove? Well, we know when you boil water, it stays at 100 degrees Celsius. So that must mean that must be an isothermal process. What about pumping up a bicycle tire? So is the temperature constant? Is the volume constant? The pressure constant? So the only thing that is constant is Q. So this is an adiabatic. Another way to think about adiabatic are these are really quick processes. an explosion, pumping a bicycle tire, any kind of process that happens very fast must be adiabatic. Processes that happen very slowly are generally isothermal. What about baking bread? So you put bread into the oven, it's at a nice temperature, but it is also at a nice pressure. And so the inside of the bread has to equilibrate with the outside. And so that you could think of it as either one of these, depending on what's going on inside the bread. Is the bread getting bigger as it's being baked? Then you would think that's probably an isobaric process. But after the bread is just sitting inside the oven like this, and it's maybe just the crust is forming, then that would be more of like an isothermal when everything has reached the same temperature. So we talked about how we talked about ideal gas and how it can expand, PV equals nRT. But we didn't really talk about how solids or liquids expand. And they also expand when you heat them up. A nice way to think about how a regular object expands is that the length is going to go as its initial length. So longer objects are going to expand more than shorter objects. And times alpha, so this is our material property, and then now times delta T. So this alpha for concrete is going to be 14.5 times 10 to the minus 6 meters per Kelvin. So then what we want to know is how big are these expansion gaps going to be. So then what we want to find is this, this is delta L. Is this delta L is going to be L0, we're at 50 meter slabs. Now we plug in our thermal coefficient, which is 10 to the minus 6. And then now times delta T. So the more temperature it increases, the more we expect something to expand. So here we're going from minus 20 up to 40, so that's going to be 60 degrees. And here it doesn't matter if you use Kelvin or Celsius, because we're just subtracting things. And then 60 times this times 50, so our delta L is going to be 0.044 centimeters, 4 meters, or 4.4 centimeters. So how can we make our perfect drink? So Mary's going to mix some ice with some juice, and we wanted to end up at this 1 degrees Celsius. So this is our T final. So we have to keep track of all these different specific heats for the juice, for the ice, and then we also have to think about how this ice is going to melt. So when we originally put it in here, we have the juice and we have a couple of ice cubes in here. And then at the end, since we're at 1 degree Celsius, everything is going to be a liquid. So what we have to do is we have to melt the ice, and then we have to increase the temperature of the ice up to 1 degree Celsius. So let's look at all these Q's. So we have to raise the ice up to 0, basically to T equals 0. Then we have to melt the ice. Then we have to raise the temperature of the ice to 1 degree Celsius. And then we have to account for what's happening to the juice. So we have 4 terms here that we have to keep track of. So what we really want to know, that we should remember, is how many ice cubes. So we're going to solve for this M ice. So here let's raise the temperature of the ice, and then that's times C of the ice, and then now times delta T of the ice. So that's T final. The ice, we're going to bring it up to melting, so that's 0 minus a negative 10. And then now we're going to melt the ice. So this is the mass of the ice times the latent heat of fusion, which is our 3 times 10 to the 5th joules per kilogram. And then now we need to add on raising the temperature of the ice up to 1 degrees Celsius. So this is 1 minus 0. And then now we need to add on what's going to happen to the juice. So M of the juice, C of the juice, and now times 1 minus, and then it starts off at 20. And then all this is equal to 0. So what we're doing is we need to collect all these M ice terms. So we're going to have our latent heat of fusion plus this 10 times C ice plus 1 times C water. And then this is going to be 1 minus 20, so that's minus 19. So that's 19 times mass of the juice, C juice. So if we solve for C ice, we're going to get 0.1169 kilograms. So each ice cube is 10 grams, so this would be about 11 to 12 ice cubes. So how long do you need to wait for a microwave to heat up your water for a nice cup of tea? So we're going to have to make a couple of approximations here. One is that, what is the power of our microwave? And so that's about 900 watts. Then how much tea do we want to drink? Let's say we want to drink half a liter. This is quite a bit, but maybe you're sharing with a friend. So half a liter of water is going to be 500 grams. And then now our specific heat of water is 4.184 joules per gram Kelvin. And then now we need to think about what is our initial temperature. Let's just say it's about room temperature. And then how hot do we want our tea? Well, I don't want it to be boiling. I just want it to be hot enough. So then I need to put all this together. So if I'm thinking about power, power is work over time. So what I really need to think about is how much energy I need to supply over amount of time. This energy that the microwave is providing is heat energy. So I'm going to look for Q. So the Q, in order to heat everything up, it's going to be MC delta T. When I plug that in, I'm going to get 121,336 joules. So this is 121 kilojoules worth of energy. So that's quite a bit. So then what I'm really looking for is this time. So then P is work over time. And then I'm solving for T, so that's work over the power, which is our 121 kilojoules all over our 900 watts. So when I plug this in, I'm going to get 135 seconds. So this is about 2 minutes, but a microwave isn't 100% perfect, so you can probably expect to wait about 2.5 to 3 minutes for your cup of tea.